In section 3.2, we're going to talk about differentiability and continuity. And we're going to talk about where functions are differentiable and where they aren't. A function will not have a derivative at a point, p, which equals a f of a, where the slopes of the secant lines fail to approach a limit as x approaches a. So for example, if I had a smooth curve like this, and here was my point a f of a, and if I was to draw tangent lines coming from the right approaching this point, notice that the tangent lines coming from the left are approaching 0. And if I approach the slopes of the tangent lines from the right are also approaching 0. So this will be, there will be a derivative at the point a f of a. Now, if these tangent lines from the left and right don't approach the same slope, then there won't be a derivative. So for example, we will not have a derivative at a sharp corner because the slope on the right-hand side is always positive and the slope on the left-hand side is always negative. Similarly, we will not have a slope or derivative at a cusp, we call this, because the slope on the left is going to negative infinity, and the slope on the right is going towards positive infinity. A vertical tangent, so if I do a tangent line right in the middle, I'd get a vertical line, and a vertical line is undefined. And at any discontinuity, we will not get a derivative because the slope from the left will not equal the slope. Well, the slope from the left could be approaching the same value as the slope from the right, but any discontinuous function cannot be differentiable. Okay, my class watched this video in the class, and I'm just going to go through it with you instead of watching the video so you can hear some sound. And we're talking about differentiability and continuity. So it's asking us, first of all, is the function g of x equaling x squared differentiable at x equals 1? Well, the first thing you need to do is show that it is continuous at x equals 1. So we have to prove that it's continuous at x equals 1. So first of all, we have to say, is there a value of the function at 1? Well, yes. The value of the function at 1 is going to be 1 squared, which is 1. Second thing we have to show is there a limit as x approaches 1 of the function x squared? At 2 is 1, so therefore, by our definition of continuity, since g of 1 is equal to the limit as x approaches 1 of g of x equals 1, therefore it is continuous at x equals 1. So we've proven that it's continuous. So now we have to show that the left and right derivatives are the same. So I'm going to use the definition of a derivative at a point. So we're going to find the limit as x approaches 1 from the positive side of f of x minus f of a over x minus a. So this is going to be the limit as x approaches 1 from the positive side. Well, the function is just x squared minus, if I plug 1 into the function, it's going to be 1 over x minus 1. This is going to be the limit as x approaches 1 from the positive side of x minus 1, x plus 1 over x minus 1. And now these are going to cancel. And if I plug 1 in for x, I get 1 plus 1, which is going to equal 2. So the limit coming from the right is equal to 2. Or the derivative, sorry, coming from the right is equal to 2. So now we're going to do the limit as x approaches 1 from the left. Again, I'm going to plug into the same equation, and because I only have one function, this is going to be exactly the same. And again, if we work this out, it'll be the same approach. We'll also get 2, so therefore, this function is differentiable at x equals 1. In the next example, we have a piecewise function, and the piecewise function was 2x when x was less than 1, and x squared plus 1 if x is greater than or equal to 1, and we want to know if it's differentiable at x equals 1. Well, first thing again we have to show is that it is continuous at x equals 1, because if it's not continuous at x equals 1, then it can't be differentiable. So therefore, I'm going to find out, first of all, is there a value of the function at 1? And I'll have to use the bottom function to evaluate that, and it equals 2. Statement 2, is there a limit as x approaches 1 of h of x. Well, I'm going to have to do the left limit and the right limit because this thing is approaching different things from the left and the right. From the left, I'm going to use the function 2x. And from the right, I'm using x squared plus 1. So plugging a 1 in here, I get a limit of 2. Plugging a 1 in here, I get a limit of 2. So therefore, the limit is 2. So therefore, I have statement 3 now that h of 1 is equal to the limit as x approaches 1 of h of x equals 2. Therefore, this thing is continuous at x equals 2. Okay, so I've shown it's continuous. So now I can try to show if it's differentiable. So again, I'm going to use the definition of a derivative at a point coming from the left and the right. So I want to look for the limit as x approaches 1 from the left of f of x minus f of 1 all over x minus 1. So this is going to be the limit as x approaches 1 from the left. Coming from the left of 1, I have to use 2x. And if I plug 1 into my function, I get 2 all over x minus 1. So this is going to be the limit as x approaches 1 from the left. If I factor 2 out, that, now my x minus 1's cancel, and my limit coming, my derivative coming from the left of 1 is 2. So now we're going to do the same thing, but I'm going to be approaching 1 from the right. So coming from the right, I use the function x squared plus 1. And again, I'm subtracting f of 1, which is 2 over x minus 1. This is going to be the limit as x approaches 1 from the right. The numerator really becomes x squared minus 1 over x minus 1. And this will be the limit as x approaches 1 from the right. And if I factor the top, it's x minus 1, x plus 1 over x minus 1. Now these cancel. And if I plug a 1 in, I get 1 plus 1, which is 2. So since the derivative from the left and right are the same, and the function is continuous at 1, yes, this function is differentiable at x equals 1. Okay, and the next thing, or next example, it says just because the function is continuous does not imply it's differentiable. And again, there's another video that the AP board shares with us, but again, I'll just work it out for you. So it says the function f of x equals the absolute value of x, and they're asking us if this is differentiable at x equals 0. Okay, well, first of all, we have to figure out if the function is continuous at x equals 0. Okay, and again, we know the definition of absolute x is going to be equal to x if x is greater than or equal to 0, or negative x if x is less than 0. So, therefore, number 1, to figure out if it's continuous, I have to show, number 1, that there is a value of the function at 0, and when it's 0, it's 0. Second thing is I have to find out, is there a limit as x approaches 0? So because it breaks at 0, I need to do the limit from the left of 0 and from the right of 0. Coming from the right, I use x. Coming from the left, I use negative x. Plugging 0 in, I get 0 and 0. And since the value of the function equals the limit, which is 0, therefore we can conclude that this is continuous at x equals 0. So we've shown it's continuous at x equals 0. Now, we want to figure out if it's differentiable at x equals 0. So again, I'm going to use the limit as x approaches 0 from the positive side of f of x minus f of 0 all over x minus 0. Well, coming from the right, I'm going to use x in terms of f of x. So this is going to be the limit as x approaches 0 from the right of x minus 0 over x minus 0. And this ends up being 1. Now I'll do the limit as x approaches 0 from the left, f of x minus f of 0, x minus 0. And, oops. And if we do that, in place of f of x coming from the left, I'm going to put negative x. So it's the limit as x approaches 0 from the left of negative x minus 0 over x minus 0. And this is going to end up being negative 1. You can see the derivatives are different on either side. So therefore, this is not differentiable at x equals 0. So, just because a function is continuous doesn't necessarily mean it's going to be differentiable. All right. In the third video on the AP board, they kind of draw our attention back to a previous example that we did in this first video. And I gave this function here, but now they gave h of x is equal to 2x when x is less than 1, and x squared plus 1 when x is greater than 1. And they asked us to find if it's differentiable. Well, if we went through the left and right derivatives, we would find that the derivatives are the same. They're 2. So some students might conclude that this function is differentiable at x equals 1 because the derivative from the right equals the derivative from the left. However, because there is no equal 1 here, this function is not continuous at x equals 1. So therefore, there is no way that it can be differentiable. So you have to be careful when you're given a function to make sure, first of all, it is continuous. You have to prove that it's continuous first. Okay, this is an AP multiple choice exam question, and it says the graph of the function f is shown in the figure above, and it has a vertical tangent at the point 2, 0, and it has a horizontal tangent at the point 1, negative 1, and 3, and 1. For what values of x between negative 2 and 4 is f not differentiable? Now they're really throwing a lot of information here at you. They're talking about a vertical tangent, and they're talking about horizontal tangents. Well, horizontal tangents, you can have horizontal tangent lines. Those slopes are just 0. So those are okay. So the only place where this thing does not have a derivative is going to be at the vertical tangent line of 2 and where it's discontinuous. So the answer would be 0 and 2 only. Now, differentiability implies local linearity, okay? So a differentiable function is sometimes referred to as locally linear, and this is that is, the graph of the function will straighten out if we zoom in to a point where the graph has a derivative, okay? So basically, if I was to look at the graphing calculator, and I'd have to load up my graphing calculator here. Just give me a second. My calculator comes into the viewing window. And the calculator that we're using in this class are the TI Inspires. Okay, if we take a look at the calculator here, let's just move this window over if we can. Actually, if I go to my calculator right here, I'm going to go to the graph. And if I graph the function, say, x squared, I am going to get a parabola, obviously. And if I zoom in on this point, okay, so I am just going to zoom in. And zoom in, we're going to go menu, zoom in, number 3, and we're just going to keep zooming in at the origin. And notice you'll see that the graph, when you zoom in, actually straightens out. So since it's straightening out at 0, that means that the graph is differentiable at 0. Okay, so let's go back to our standard window. And now let's take a look at the function, the absolute value of x. And to get the absolute value of x, I'm going to go right here. Where's my absolute value? Right here. And I'm going to put x in there. And enter. And if we zoom in on the red graph now, you'll notice as we zoom in, the blue graph is flattening out, but the red graph is not flattening out. It's not locally linear, so therefore we cannot take the derivative of the absolute value function at x equals 0. And we showed that earlier in the lesson. So there's a good visual of what local linear means. Okay, so that pretty much concludes our lesson. Okay, the last thing is we want to learn how to do the derivatives on a calculator. So again, I'm just going to load up the calculator here again, and I'm going to show you how to find the derivative on the TI Inspire. As part of the calculus course is you need to know how to use a calculator. So our function that we were dealing with was x cubed when x is, we wanted the derivative of x cubed at x equals 2. So we want to calculate, so menu, oops, we want to get to the calculate screen. We're going to go menu. There's a couple ways we could do this. Derivative at a point, and we have the x value that we're calculating at is 2. And now our function, we just type in, was x to the power of 3. And I hit enter. So that means if I took the derivative and evaluated at 2, it would be 12. Okay, so that's how you do the derivative at a point. Okay, my other function was 4 root x at 6. So again, menu, calculus, derivative at a point. We want the x value of 6, and my function this time was the square root of x. And it would be root 6 over 12. And you could even change that to a decimal if you wanted to, and it would be 0.204. Okay, so that concludes section 3.2. So there's your assignment on page 111, numbers 1 to 10. Again, if you have any questions, check the black binder in class that has all the answers worked out.